Okay, let's get started. We're going to continue with chapter 10. Lots to get through today. It's going to be very fast-paced, a lot of writing. So today we're going to talk about uncountable sets and how they sort of relate to countable sets and enumerable sets. We're also going to talk about some relationships between them and talk about cardinal numbers and how the size of different sets relate to each other. And we are going to do a lot of proofs of important theorems. We won't prove everything, but if the proof is short enough, then it sort of shows a really good idea, we'll go through it. And otherwise, if it shows a really good technique, we'll go through that as well. But last time we talked about denumerable sets, and we showed that all sorts of sets were denumerable: the rationals, the integers, the positive integers, any infinite subset of these guys. So now we're going to talk about the uncountable sets. The most familiar one would be the real numbers, but there are, of course, many others, right? So first, some remarks on decimal expansions. So to sort of understand some of the arguments we're going to be using, we have to remember some things about decimals. So one type of decimal expansion you can have is the finite decimal expansion. So for example, we can write a half as 0.5, or we can write 1/8 as 0.125. Right, they're just a finite number of digits. Right, so that's one example. Two. Another kind of decimal expansion we can have is infinite repeating patterns. So an example of a decimal like that would be something like 1/9 is an example. That guy is like 1, 1, 1, 1, 1, 1, 1. And that pattern just repeats forever. Or another example would be something like 7/11, and that's actually just a pattern of 63 repeating forever. 6, 3, 6, 3, 6, 3, 6, 3. And that literally repeats forever. Right? So there's just a pattern of 63. Sometimes people write this as 63 with a bar on top to say, this guy just repeats that number forever. Another kind of decimal expansion we have for example, it turns out a half we can write as 0.5, and we can choose to put infinite zeros behind it, but it's also actually the same as 0.4999999. Because you can actually prove, and I'm pretty sure you did this in calculus 3, that 1 is actually equal to 0.9999 forever, right? So you can have a number with two different decimal expansions that repeat in some way. So for example, 1, you can just have 1.00000, but that's actually equal to 99999 forever, right? So there's a way you can express any decimal as two different ones. So to just mention this in the future to avoid ambiguity. We will use the expansion that ends with 0, 0, 0 forever instead of 9, 9, 9, 9, 9 forever when uniqueness is a concern. But just so you know, it's possible for two decimals to have unique expansions. There's a fourth type, which is the infinite non-repeating. An example of that is pi it doesn't repeat. There is no repeating pattern. E is also one. So it's 2.7182818. It seems to repeat 2818 after a while, but it actually doesn't repeat it forever. It repeats 281828, and then it starts going different. 49045. And it doesn't repeat anything else. So those are the four main types that we'd like. Some things to note. Q is precisely all decimal expansions of types 1 through 3. The set of irrational numbers set of all expansions type 4. Right? It's no coincidence that when I was giving you the examples here, I could write rational numbers on the other side of the equation. It's because rational numbers all have these patterns. They're either finite, you can write them in two ways by repeating zeros or 999s, or they have infinite repeating patterns. Rational numbers all do this. Irrationals don't, right? They do not have repeating decimal expansions, and they're all infinite. R, we know, is this guy, which is the set of all decimal expansions. We're going to use this idea to our benefit. So the first theorem I want to prove is that R is uncountable. Well, ultimately I want to show that, but we're going to show that as a corollary of something else. Let's first start with the interval 0, 1, which is usually the first thing people start with when we show this. Is an uncountable set. We're actually going to prove that the interval 0, 1, all the real numbers between 0 and 1, there are an uncountable number of them. There is an infinite number, but we cannot find a bijection between that set and the natural numbers. In fact, later on we're going to show there are actually way more in this set than there are in the natural numbers. So let's do the proof. It's a very famous argument. We will use Cantor's, the German mathematicians, diagonalization. We're going to prove this is uncountable. Note that all elements of 0, 1 have the form 0 point, let's say A1, A2, A3, A4, A5. Where the AIs are elements of 0, 1 all the way to 9. Right? So these are just decimal expansions that start with 0, and you can have a different set of digits. You might have a finite number, an infinite number. You can have any one of those 4 types, but every number in this domain, in this set, you can write in this form. Right? So we're going to use that to our fact. So now, assume to the contrary, 0, 1 is countable. I.e., it's infinite, of course, the numeral. Right? Then we can write 0, 1 as just a list of elements, right? A1, A2, A3. And there exists a bijection F from n to 0, 1 such that f of 1 will give us A1, f of 2 will map to A2, f of 3 will map to A3, f of 4 will map to A4, and so on and so forth. We can actually list these guys, and there's a function that maps the n to these guys, right, in some particular order, right? So let me just write what the form of this one looks like. So let's call this 1, 2, 1, 3, 1, 4. Right, those are the digits. 2, 1, 2, 2, 2, 3, 2, 4. Those are the digits. 0.31, 32, 33, 34. Those are the digits here. 41, 42, 43, 44. Where all the AIIs are digits. So we're going to do a proof by contradiction. We're going to assume that it's actually countable, which means we can list all the elements, and there's some bijective function that maps 1 and 2 and 3 and so on to all these elements. And this, of course, goes on forever. So we're going to find a contradiction to this, right? So we pretend here we have a list of all elements in 0, 1. So pretend we can exhaust the list with this bijective function f. Right? Now how we're going to get the contradiction is we're going to show that we can find a decimal expansion that is actually not in this list. Right? So it's sort of the idea that we used to prove the infinitude of primes, where we assumed there was a finite list, but then there's always one more guy. We're sort of going to do the same idea. So we're assuming there's an infinite list, but we're still missing someone, meaning that f cannot be onto, which means it's actually not a bijection. Right? So what we're going to do here is create a decimal expansion. B equals 0, B1, B2, B3, B4. Where the BI's are just digits. In the following way. I'm going to define the digits in this way. BI is going to be 1 if your AII is 2, and set it to be 2 otherwise. So basically, I'm going to create a decimal where it's going to look at all these diagonals, right? So I'm going to look at this guy, and I'm going to check, is it equal to 2? If it is equal to 2, I'm going to change it to a 1. And if it's not 2, I'm going to change it to a 2. Then I'm going to look at this guy. Is it equal to 2? If it is, change it to a 1. If it's not equal to 2, change it to a 2. Look at this guy. Is it equal to 2? If yes, change it to 1. If it's not equal to 2, change it to 2. And I'm going to do this all the way along the diagonal. This is why it's called a diagonalization activity. You're looking at the diagonals of this list, right? And basically what you're doing is you're going along the diagonal and you're going to be changing these numbers, and then BUI is going to be the list of the decimal expansion with all these different numbers changed. Right? So, do I need to do an example, or do you guys understand what I mean? Right, so, example. Let's say in my list, let's say, pretend the order that I gave it was something like this. So this is 0.5789234, and this was 0.11234785, and this one was 0.79823.49. We're just putting a random list. 3, 2, 1, 6, 7, 8, 2. We can do all these numbers like this. Then what B is going to be is it's going to look at the first digit, look at the first number, and look here. Notice that this is not equal to 2. Therefore, in my B, I'm going to put a 2. Then I'm going to look at the second digit in the second number of the list. Notice that it is not equal to 2, right? So I'm going to change it to a 2. Then I'm going to look at the third number in the list. It's not equal to a 2, so I'm going to change it to a 2. Let me actually... Right? When I go to this one, and I look at the fourth number in this list, it's actually equal to 2, which means I'm going to change it to a 1. Right? So the B is just going to be a decimal expansion that only has 2's and 1's in it, and it's going to have 2's and 1's based on what the diagonal element of my list looks like. Right? So I'm just going to look at these numbers and start changing it to a 1 or 2 according to this rule. Right? So that's how I'm creating this decimal expansion. So it's simply a list with only 2's and 1's assigned in this fashion. So now here's the important part. Note BI, what it does, it actually changes this digit. If it's a 2, it changes it to a 1. And if it's not a 2, it changes it to a 2. So what you notice is that BI will not be equal to AII for all I, because I'm actually changing its value. This means that B will not be equal to any of the AIs for all I and N, since it is different in the ith digit. This will of course mean B is not in the range of my function, which would mean F is not onto. And we have a contradiction. So basically, if I assume I can list all the numbers in 0, 1, and I can write on the list, I can always find a guy that's not in the list. And even if I put this guy in the list, I can do the same process again and find another guy that's not in the list. Right? Every time I create a list, infinite, no matter how many terms it has, I can create another number that just changes all the guys on the diagonal, and that will be a new number, right? I'll never be able to exhaust all the decimal expansions by listing them, right? And which means 0, 1 is not countable. Of course, I'll mention that. So that's the first thing. Now, note that 0, 1 is uncountable can show us that R is uncountable. Here, proof. Note that 0, 1 is actually a subset of R, right? It's an interval of real numbers. If we assume R is countable, i.e., in this case, since it's infinite enumerable, then this would mean 0, 1 is countable. Why? Right, we actually proved last time. Right, we actually showed last time. We showed an infinite subset of a enumerable set is also itself enumerable. Right? So this would mean 0, 1 is not uncountable, which is a contradiction. We just proved it was uncountable. Right? So R is uncountable. Yes?
So to prove 0 to 1, there's an infinite number, I guess. Can you just...
Oh, to know that this is infinite? Well, we can use the denseness of Q property from test 1. Right?
Yeah.
So I can pick any two numbers, any number that's greater than 0 but less than 1, make an interval, and I can always find a rational in there, and I can find infinite number of them. So I know, yeah.
And then find a number half of that, half of that.
Yeah. So I know that there are at least an infinite number of rationals in here. So I definitely know it's an infinite set. Right? Now the idea is it is a countably infinite set, and the answer is no, because if I try to list everyone, I'll always miss something. Right? So I know it's uncountable. I actually can't count it. I can't write all the numbers here as a list. Right? And knowing that means I can't write all the numbers in R as a list, because this is a subset of R.
Could you also prove it by, could you also prove that R is uncountable and by making just a bijective function from 0 to 1 to R?
Yes, we're going to actually do that later. I'm going to prove that R has the same size as that interval. Yes. That's coming, right? Which is, it's sort of crazy, but yes, there are as many real numbers in general as there are between 0 and 1. Which means not only is R larger than the natural numbers, it's insanely larger than the natural numbers. Like, we have more real numbers between 0 and 1 than there are natural numbers in general. And it's really crazy. So, when do I prove that? Right, I sort of jumped the gun with that one. I actually wanted to prove the general statement. My general plan was to prove this general statement, and then that's just a corollary, but it'll work out. We'll actually just redo this theorem in general. That A, B sets with A is a subset of B. Then, if A is uncountable, then B is uncountable. Pretty much the same proof, except now I can actually do this in general. In general, I can know that an infinite subset, the subset of an uncountable, if an uncountable set is a subset of some other set, then that set must also be uncountable. It's sort of the Pythagorean theorem. I think I actually wrote down the exact theorem. In your textbook it's theorem 10.4, but we also proved it in last class. And that gives us the contradiction. And so with that theorem I could say, since 0, 1 is a subset of R is uncountable by this theorem. I could have just said that. Right? So it's actually true in general. What? Well, it can work either way. Well, the contrapositive, I have to worry about the finite case and all that stuff. Sorry. Okay, so another very important proof. We're actually going to see later on there are different classes of uncountable sets. You can have two sets that are uncountable, but they're actually not the same. One can be larger than the other in some sense. It turns out that this is not true for denumerable sets. Every two denumerable sets will actually be numerically equivalent. They will have the same number of elements. What I'm saying is, i.e., if A and B are denumerable sets, then the size of A is actually going to be the same as the size of B. All right, so there's only like one class of denumerable sets as far as size is concerned. Proof. What does denumerable mean? Come in. Okay, what does it mean for its cardinality to be the same as n?
You can put it in a one-to-one relationship.
Right. There exists a bijective f from n to a. Right? And since b is denumerable, there exists a bijective function, call it g, from n to b. Then what we can do is we can actually take G of F inverse, right? This will be a set that goes from A to B, right? And it is a bijection. Because we proved 2 classes ago, if you have a bijection, then its inverse is a bijection, and the composition of 2 bijections is also a bijection. So if I take F inverse, I get a bijection. I compose with G, I get a bijection. So it turns out that if I know that there's a bijective map from N to A, and there's a bijective map from N to B, I can find a bijective map from A to B. In particular, this is a map from A to B. And it is a bijection, which means A and B have the same size. So yeah, any 2 denumerable sets have the same size. This is not true for uncountable sets. So let's see. Another proof that I want to do here. Like I said, a lot of facts, a lot of variety today. Okay, so I want to prove if A is enumerable and B is uncountable, then A does not have the same size as B. If A is uncountable, and B is enumerable, doesn't really matter in this one, but that's how I have it in my notes. Let's keep it enumerable. And B is uncountable, then A and B do not have the same size. No denumerable set has the same size as an uncountable set. So here's a proof. Assume to the contrary that A is equal to B. Then that means there exists a bijective F from A to B. But this would mean that B is countable. Because it turns out you'll be able to deconstruct this map in this way and obtain a bijection between B and N. And so that can't be true. We have proven that R cannot be equal to N because we know that R is countable and N is denumerable. So this says they can't be equal. But I know R is greater. Why? Because in the first step, I proved that the function cannot be onto because it's always missing someone. So that R has more elements than N does, than any countable set does. There are many ways we can prove this, by the way, but this is just one thing you can conclude from just the theorems that I proved so far. It turns out proving this in general is actually not, well, it's not hard, but it's not. To prove that in general any uncountable set is greater than any countable set, you actually need something called the axiom of choice, which we'll talk about later. But we'll get it. So, yeah, so we know that the interval 0, 1 is uncountable. We know that R is the same as the interval uncountable, 0, 1 in terms of size, and r is uncountable. We know that r cannot be the same size as any denumerable set. In fact, with this theorem, we know that r has to be greater than the size of any denumerable set. And once it's greater than n, it's fine, because every two denumerable sets have the same size. So if it's greater than any denumerable set, it's greater than n in terms of size. So that's, yes.
For the cardinality of the real numbers is greater than cardinality of natural, can you prove it by saying that since it's kind of like, I guess, which one the rate is faster, or like the real numbers?
How do you mean the rate is faster?
Like, and the natural numbers you're counting one by one, so it's like n, but the real numbers, I guess using like the denseness of q, you could say it's like 2 to the n or something like that. So, and 2 to the n, I guess diverges faster than n.
Okay, I don't understand how those functions come into play. Because if you want to use the denseness of q, it's also true for me to say that r is greater than q, right? But then, if you're using q itself to prove your claim, how is that going to... Right, because these are actually the same size, remember? So sort of replacing n with q doesn't really help. But yeah, in terms of rates, it's going to be very difficult for you to do that. You'll have to probably bring functions into play, and then what you're thinking of would be functions on the real numbers as opposed to functions on the natural numbers, and that sort of complicates things. There are other ways to prove that r is bigger than n, but
wasn't there something like we did that off or something? There's like symbol 2 to the...
Yeah, just that
I was thinking...
11 null is,
Yeah.
or 2 to the 11 null.
right,
is
yeah.
15.
So we didn't think of those as rates though. Remember, 2 to the aleph null was actually a set of functions. It wasn't rates. We're going to actually talk about that. We're actually going to prove, well, I'm not going to prove, because the proof is actually a bit longer, but we're going to prove that r is actually equal to 2 to the aleph null.
If you multiply real numbers by some integer, the cardinality of that will be the same as the cardinality.
In fact, if you take a bunch of sets that have the same size as the real numbers, and you add a countable infinite number of them, take a union, you get the same size as the real numbers also. A countable union of uncountable sets is actually the same size as the individual sets. It will actually be the same size as the largest uncountable set in the union. Anyway, let's move on.
Can you say a countable set as a subset of an uncountable set?
No, that would depend on the elements. It would depend on the elements, right? Remember, subset means the elements in here are also in there. So it depends if the elements are distinct. But we're actually going to talk about a little bit about the idea of think you're reaching for, which means for one set to be less than or equal to another set in terms of size. Your question might sound simple, but it actually involves the axiom of choice actually answering this also. Okay, let's do another thing. To prove in general. Here's another theorem. Let A and B be real numbers with A less than B. Then it turns out that the size of this interval, the number of elements in that interval, is actually the same as the number of elements in all the real numbers. And proof, it's actually a homework exercise. So you're going to prove this. I do want to give you some concrete examples though. So I wrote down a bunch. So, first example is using f from, say, 0, 1 to r by f of x equals 1 minus 2x over x squared minus x shows that the interval 0, 1 is actually equal to r numerically, since f is a bijection. It's not hard to prove that f is a bijection. I can leave that to you. It won't be bad to prove that f is 1 to 1 and onto. So I can actually map the interval 0 to 1 to r by using that particular function. Also, I can say f, let me actually do this, call this f1, call this f2. I can map minus 1 to r. I can actually map it bijectively to r by f of x equals x over 1 minus absolute value of x is a bijection. So the interval minus 1 to 1 is the same as the size of r. Right? I can actually pair off all the elements and both sets will be exhausted at the same time. F3. This is another example from 0 to 1 to r. But it's an example I like because let's do a tangent function of pi to 1 x minus a half is a bijection. I like that one because you can go all the way back to pre-calc. Tangent was one of the first functions you learned that you can have a finite horizontal interval going to all real numbers from positive infinity to negative infinity. Right? So if you look at tangent of x, notice that between pi over 2 and minus pi over 2, your y value actually hits all real numbers. Right? So you have a finite length interval actually mapping to the whole real line. Right? So you can actually map the interval. So this guy shows that you can map minus pi over 2 to pi over 2 onto r bijectively. So it's one of that first guys. And then in pre-calc you would have learned that if you have y equals a tangent k x minus b plus c, then b would be the center, and you know that the period would be pi over the absolute value of k, which means I can actually force my tangent. If I look at tangent of pi times x minus a half, what this does is actually it forces my function to happen between 0 and 1. The center is going to be that half, and the period is going to be pi over the absolute value of pi, which is 1. So I know the whole thing will happen within an interval of length 1, and the center will be a half. I can actually set that up. And so the book actually shows you how they set up these guys, these functions, but back when I was doing this class, the function I thought of doing it with was the tangent function, because I don't know how it behaves. So that's an example I like to use. But the book actually shows you how they set up the polynomials. You can read through that if you like. Here's another way to figure this out, which is sort of helping you with your homework, I think. If I look at F4, I can actually map 0, 1 onto the set minus 1, 1 by f of x equals 2x minus 1. Right? And And that's a bijection. So if I look at F5, which does something like F3 inverse, which goes from R to 0, 1, composed with F4, that would be a function from R to -1, 1. Did we actually show? So in your homework, that's sort of how you're going to want to do it. So for homework, what you're going to do is show you can map 0, 1 to any interval of length AB bijectively. And then do a composition from this guy to get to R by connecting one of these functions that you already know. And actually mapping this to that bijectively is not, it's a lot easier than you think. I think how to parameterize a line segment from Calc 3. Right? And it's really crazy. Your AB can be any real numbers. I can say something like 0.1, 0.11. Right, the two numbers, all the real numbers between those two guys are the same as all real numbers in general, right? It doesn't matter how close these numbers are together, right? It's a crazy amount of numbers. What else can we say? Okay. Now we're going to talk about comparing cardinalities. First, we're going to start with a theorem. For any non-empty set, well, it actually works in general. But let's do non-empty sets. For every non-empty set, the size of the power set of that set is actually equal to the sum of all functions, the size of the set of all functions from A to 2. Right? So remember this guy. You think of as the set of all functions from A to the set 0, 1. So if you look at all functions from A that maps to the codomain 0, 1, and you look at all possible functions, that's the size of all, the number of those functions will always be the same as the number of elements in the power set. And it's for everything, so it will go for infinite sets as well as finite sets. So let's actually prove that. The hardest part with the proofs like this is actually figuring out what function you want to use. So let's do this. Define function phi from the power set of A to 2 to the 8 by P of S equals Fs. Where Fs equals 1 if x is in S, and 0 if x is not in S, for all x in A. And S is just some subset of A. Right? So this function is going from the set of subsets of A to the set of functions that map from A to 0, 1. And I define it that if I plug in an element here, the output will be this function, which goes like this. So for example, I want to give an example. Let me do an example of showing you what this function actually does. So say A is the set AB, then we know that the power set of A would look like the empty set, the set containing A, the set containing B, the set containing AB. Right? So we have 2 elements in A, the power set will have 4 elements. Right. So these guys are like the S's, right? So these guys are the S's. Right? So S can be this, or S can be that, or S can be that, depending on which guy here. This S represents any subset of A, right? So what we can do is, for example, if S equals the empty set, then Fs would just be F of the empty set, right? And what this function is actually going to do it's going to look at all elements of A, and what it's going to do, the output is going to be 1 if X is in A, but it's going to be 0 if X is not in A. Right? So in this subset, is the A in this subset? The answer is no, so the output is 0. Then it looks at B in A. Is B a member of this subset? The answer is no, so it's going to put a 0. Or if I look at, if S is actually the subset A, then Fs would be F of A. So it's going to go for all x in A, it looks at the element A. Is A in this subset? The answer is yes. Therefore, the output is a 1. B. Is B in this subset? The answer is no. Therefore, the output is a 0. Right? So it puts 1 and 0 based on whether it's in the subset or it's not. Right? So let's say it was this guy. What would the function f sub b look like?
A0, B1.
A0, because A is not in here, so A maps to 0. B is in there, so B maps to 1. If S is the subset AB, then Fs would be equal to F of AB, which would be what? A maps to 1 and B maps to 1. Right? Because A is a member of the set and B is a member of the set. So for every A in X in A, X is a member of the set, so they all map to 1. What you'll notice is that this actually exhausts all possible functions from A to the set 0, 1. Right? These are all the possibilities. And we've exhausted at the same time all the subsets. What we're going to try to prove is that this will work in general. Whether you have any finite number of sets or an infinite number of sets, this is going to work in general. And we're going to show that by setting up our functions this way. So our function is simply going to be a rule that verifies whether an element of X is in the particular subset we're looking at or not. So let's continue. So first we note that fs is actually in the codomain of this function, since the range of fs is the set. Since the codomain is the set 0, 1. So notice that fs, I know for all of these guys, they're actually in 2 to the 8. Right? That's going to help us prove with the onto part. So let's first show that phi is 1 to 1. Right? So I define a function from the power set to the set 2 to the 8, and I'm going to show that it's 1 to 1 and onto. So phi is 1 to 1, so assume that phi of s is equal to phi of t, where s and t are subsets of A. Right? So let's say the output of two subsets actually give us the same value. Okay? And this means that phi of s of x is equal to phi of t of x for all x in A. Right? Two functions are the same if their outputs are the same for all inputs. Right? But this would mean phi of s of x equals 1 if and only if phi of t of x equals 1. They have to give you the same output all the time. But that would mean, when would this give you 1? Well, it's if x is a member of S, right? So this means x would be a member of S if and only if x is a member of t. Therefore, we have obtained that s is actually equal to t. Because this actually proves that s is a subset of t and t is a subset of s. So phi is actually 1 to 1. Any questions on the 1 to 1 part? So I just assume the outputs for two subsets are the same. Well, it just means that all coordinates must be the same. So for each x, they must agree. And so they'll both give me 1 or they'll both give me 0 at the same time. So in that case, if this one gives me 1, that one has to give me 1. But getting a 1 means that your x is actually in the subset. So I can get to here, which means that your s must be equal to t. Right? For the onto part, assume f is in 2a, then so basically, if I am given some function, I just know that that function, all I have to look at is the subsets here. Right? And I just define the set S to be the guys that give me 1 here, and it turns out that fs will actually be equal to that function. So I'm just sort of going backwards with my example there. So, actually proves it wrong. So I wanted to show you guys this proof. It's It's not super long, but it's actually a super important proof technique. Like, people do this all the time. Just use functions to count stuff. And a lot of times they use sets to count the number of things that fulfill a certain property, and you use that to your advantage. It's sort of a nice technique to know. It's also sort of hard to digest, I know, but if you read it slowly and carefully next time, and sometimes do some examples, it will actually help you to make things a lot clearer. Some remarks here. A lot of info. For sets A, B, there exists a one-to-one function f from A to B. You write that A is less than or equal to B. Other than that, I want to introduce some notation. Called aleph null or aleph not. It's actually a Hebrew letter, aleph. The size of R is denoted by a lowercase c, and c is called continuum. Numbers like aleph null and C basically, these numbers just describe the cardinalities of sets. these guys cardinal numbers. And you would devote a lot of times to cardinal numbers and cardinal arithmetic in a graduate set theory course. It's actually a very important idea. So, important mark is this. You can prove that one guy is at most the size of another guy if you can find an injective function from one to the other. Right? So for example, we know that n is less than or equal to the size of r because we can actually do the identity map from n to r, which actually is an injective function going to r. But we can't find an onto function, so that's why we can know that n is less than r. Because you'll miss a lot of elements if you just do any function from n to r. Another cool topic, it's actually a pretty open question, it's called the continuum hypothesis. Basically, we assume there exists no set S such that the size of S is strictly between N and C. Meaning, N is sort of considered to be the smallest infinity that we know about, and the next highest infinity that is greater than N is C. We don't think there's anything in between. And it's a hypothesis, meaning it's never been proven, it's just something that's always assumed. In fact, the situation is more dire than that. It can be shown, and two mathematicians shown this separately. It turns out the current rules of set theory that we have are just not comprehensive enough to actually figure this out, right? So someone actually proved that, you know what, we actually can't prove whether this is true. And then someone actually showed later on that we actually can't prove it's not true either. So you can't prove it's true, you can't prove it's false, so we don't know, it's a hypothesis. We think this is the answer. It just makes all the sense in the world for some reason, but strictly speaking, we actually can't prove that this is the case. All right, so this is the smallest infinity that we know about. The next largest one is C. There is no infinity in between these two. That's our guess, our best guess. So here's a question. Does there exist S such that the size of S is greater than C? Right? So we know about these two infinities. This is the smallest one we know about. There's no one in between that and C. C is the cardinality of the real numbers, which we know is greater than this. But is there someone greater than that? Is there a bigger infinity than the bigger infinity to the smallest infinity that we know? Turns out the answer is yes. there are infinities that are larger than the infinity of the real numbers. And one of the first ways that you prove this is during the following theorem. If A is a set, it turns out the size of a set will always be smaller than the size of its power set. That's true for finite sets clearly, but it's also true for infinite sets as well, right? Which means if we know the cardinality of R, we take the power set of R, it turns out the size of that set is actually strictly larger than R, so we can get bigger than R. And then we take the power set of R, that's actually larger than this guy. And we can actually keep doing this. We can actually take power sets forever. And we'll always keep getting bigger and bigger infinities, strictly bigger infinities, right? So it turns out that infinities can get quite huge, and we can show that there are an infinite number of infinities, and they're not the same as any of the others. There's an infinitude of infinities. And not all of them are the same size.
But is the size of the infinity of infinities, is that null or is that C?
The size of the infinities of the infinities.
Is it enumerable?
I think to answer that you need like axiomatrix. But we're not going to go that far. That's sort of getting too crazy. We're definitely not going to prove that. But I don't want to say it's enumerable. My intuition is that it's more than it's larger. Our theorem. We're actually going to prove this. I wanted to get to the Schroeder-Bernstein theorem, but we're not going to make it. Don't think. But let's actually prove this. Proof. I wanted to prove this because it shows another useful technique, the idea of using sets to collect elements that you then make judgments from. Right? So if A is the empty set, then we know that the size of A is 0, and we know that the size of P of A is 1. So A is less than P of A. So assume we're not the empty set. Right? So clearly it works for the empty set, very trivial to show it. So let's assume we're looking at a non-empty set. And I'm not assuming anything on A other than it's non-empty, right? So I'm not assuming it's countable or uncountable. It's just a set that's not empty, right? We're going to show that the power set is actually larger. Basically, we're going to show what I had here but erased. We're going to show we can find an injective function from A to P of A, so that we know that A is less than or equal to P of A, but then we're going to prove that there's no way to find an onto function from A to P of A, which means that P of A is going to be larger. So we can define a function f from A to P of A, the power set of A, by just let f of A be sent to the subset containing itself. Currently f is 1 to 1. Right, because if f of A equals f of B, then A equals B, right? You just remove the set brackets. That's not going to be a problem. So we know that the size of A is at most the size of the power set, right? Because I can have a one-to-one function going from A to that by just sending every element in A to the set containing itself. Right? So now I have to show that it's impossible to actually find an onto function. So we show that there is no onto function G from A to B. And we're going to do this by contradiction, right? So assume there exists an onto function G. So assume there exists G from A to the power set with G onto. Right? What are the consequences of that assumption? Well, let me just expound on this. So, so that means for each G of A in the power set, right? The output of this function in the power set, there is an associated A in A. Such that A actually maps to G of A. I'm going to show that this breaks down. So there are going to be two cases. One, A can be an element of G of A, or A is not an element of G of A. Right? Remember, G of A is just a subset of A. I can say A is actually in that subset, or A is not in that subset. And I should probably give you an example. Say A is the set 1, 2, 3, and G is defined by, let's say G takes 1 and it maps it to the set 3. It takes 2 and it maps it to the set 1, 2, 3. It takes 3 and it maps it to the set 1, 2. So here's an example of a function that goes from the set 1, 2, 3 to the power set. It maps 1 to 3, it maps 2 to the entire set, it maps 3 to the set 1, 2. Notice that for each case we have two options. Notice that 1 maps to a set that does not contain 1, right? So that means it's case 2 here. 2 maps to a set that contains 2, so that's in case 1. 3 maps to a set that does not contain 3, that's still in case 2, right? So there are two cases for every element. Now here's going to be a useful technique. We're going to actually use a set to collect the number of elements here. Right? So let B be the set of all A's such that A is not in G of A. So for the above example, B would be the set 1 and 3. Right? So I look at the possible, all these functions, and I create a set that's going to collect all the elements that are not a member of the subset that they're assigned to. Right? So in this case, 1 mapped to the subset containing 3, so 1 is not a member of the subset I assigned it to, so 1 is a member of B. 2 maps to 1, 2, 3, it is a member of the subset it's assigned to, so 2 is not in B. Right? 3 maps to the set 1, 2, so 3 would be in B because it maps to a subset that it is not a member of. Right? So that's how I create B. So I can look at all possible functions, and then I'm using a set to collect all the elements that map to subsets that do not contain them. Right? So it turns out that this set is not going to be in the range of G. That's what we're going to prove. So G cannot be onto. Right? Note that B must be a subset of A because it's talking about the A's in A. And look at the elements in the set, which means that B is definitely an element of the power set. Right? So if I can show that it's not, if B is not the output then of any element, then it's not onto. So let's see. So since we assumed G is onto, there exists B in A such that G of B will give me that subset B. So let's examine the two cases, right? In a very similar manner of how we constructed B itself. Let's ask if this element of A that maps to B, is it a member of B or is it not a member of B? So let's actually look at that. So if we assume B is in B, then this means, what does it mean to be in B? It means you're not a member of the set you map to, right? And then that means that B cannot be an element of G of B, but G of B is B by our assumption. So B is not a member of B. Right? So if I assume B is a member of B, I conclude that B is not a member of B. That's a contradiction. If we assume that B is not a member of B, then what does that mean? This means B is not a member of G of B, right? Because G of B is equal to B. But then that would mean B must be an element of B by definition of B. So by assuming B is not in B, I have to conclude that B is in B, which is another contradiction. Therefore, G cannot be onto. Because if I assume G hits every possible subset, it has to hit this subset. But it can't hit that subset because it would lead to a contradiction if it did. So, in particular, this means that A has to be strictly smaller than the power set of A. And this is sort of a common technique. In fact, it's sort of what Bertrand Russell used to prove that there is no set of all sets. Because then he considered something like the sets that contain themselves versus sets that do not contain themselves, and he ended up with a contradiction like this. It's a very useful technique. It's also a very common technique. you want to show a property does not hold, assume that you create a set that collects all the elements for which the property does not hold, and show that a contradiction arises from that. It's a very common thing to do. It's a very nice proof technique. So there's a theorem. We're not going to prove it. But if you look at the power set of n, this is actually equal to 2 to the n. Right? This we proved in the theorem just before this one. Proved 2 theorems ago. But what's probably surprising is that this guy is actually equal to the size of R. That proof is in the text. We're not going to go through it. It's just too long and tedious to write out. But it uses the previous proof, this idea that we can get a bijective function going 2 ways. Actually, it also uses the previous theorems as well as the Bernstein theorems. Which is the last topic in chapter 10, which is going to push into next time. So from this, we can have a corollary. How we can compare cardinalities. The cardinality of n is actually less than the cardinality of p of n, right? And since the cardinality of p of n is actually equal to r, proof we can read from the book, we have that another proof that n is actually strictly less than r, right? Because r is actually the same as the size of the power set of n. So the natural numbers are smaller than the real numbers, but if you take the set of all subsets of natural numbers, it turns out that you actually have the same number of elements as there are real numbers. Also, to again answer that question that we started out with, if S is equal to the power set of R, then the size of S must be greater than the size of R. So S is greater than C. Also, you can note that if S1 is the power set of S, then S1 is greater than S, which is greater than C. And you can continue this way. If S2 is equal to the power set of S1, then you know that the size of S2 is greater than the size of S1, greater than the size of S, which is greater than C. And you can construct, in this particular way, you can construct a countable number of sets that are all bigger infinities than the previous ones. But there are probably other constructions for getting much larger sets. We'll stop there for now. Next time we'll finish up chapter 10 with the Schroeder-Bernstein theorem and also talk about the next book. You can probably start reading the next book. Most of it is not so bad. The first 3 sections are things we've done already. The main things we want to take from the next text is going to be the completeness axiom, which tells another defining property of the real numbers compared to the rationals and integers, as well as Archimedes' principle. So next time we'll cover those if there are no examples. Go over this stuff, read it very slowly.
Getting a sheet for the second exam.
Yes, I'm almost done typing up the review sheet. I will post it. in the review sheet, we're going to do a lot more comparing cardinality. So I'm going to ask you to look at sets like, n to the n, right, or r to the n, right, or 2 to the r, and comparing all of these guys. We're going to look at those. But yeah, I'm almost done typing those up. I'll post it tonight. That you'll need for Thursday.
It's going to include the national as well.
Yeah, they'll include with under review. Yeah. So that's for next time.